Welcome everybody. We've reached the final video of Open Chemistry Online, and if you've watched all the videos so far, I just want to give you a really sincere thank you to supporting this project, and I hope that you've really gotten a better understanding of chemistry and used it to maybe see the world a little bit differently. I know that my study of chemistry has really done that for me. So yeah. Today we're going to be looking at intermolecular forces, and so building off of the idea that different molecules have different geometries that we learned in the previous video, we're going to see what exactly the different types of forces that hold these molecules together could be. Whether it's the permanent polarity, the permanent what we'll call a dipole that we've seen from many of the molecules based on their molecular geometry, or in the event that a molecule is nonpolar, right, doesn't have one of those permanent magnet-like qualities to it, what exactly it is that's holding the molecules together in the absence of that polarity. And we'll also take a look at a third intermolecular force that comes up just very often in biology called hydrogen bonding, and why it is so special and why it ends up being the strongest of the intermolecular forces that we're going to discuss here. And without much more, thank you again for making it this far, and let's jump into the video. All right, we've gotten through our discussion and research about molecular geometry, even a little bit about polarity, and so now we're going to really take that one step further and see, well, now that we know more about these shapes, we know more about their permanent dipoles, what exactly are the forces that are holding molecules together? So the first intermolecular force is the one that we've kind of referenced a little bit already, right? Dipole-dipole forces. This is when we have polar molecules, right? Dipole-dipole force exists when we have two polar molecules, so two HCl's here, where we know they have a permanent dipole. And the dipoles look like this, right? We can think of them as permanent little magnets. And therefore, because they're like permanent little magnets, we feel a force between the negative side of one HCl and the positive side of another HCl. And so again, this is the force between these two dipoles, and thusly called dipole-dipole forces. And keep in mind, right, one little thing to mention about intermolecular force in general is that the force inside HCl, right, holding the H to the Cl, that is an intramolecular force, kind of like an intramural sport is one that you only do, within your college. And so those are the forces that are within the molecule, and the intermolecular force, this is the force between the two molecules. And the intermolecular force, while we're going to be talking about these generally, and we're going to talk about them as being, varying strengths, none of them are as strong as a covalent bond, right? So the intermolecular force, while it does hold molecules together, it's not as strong as the forces holding atoms together. So kind of a different, a different league of forces, nevertheless very important for the physical state and for the physical properties and even, chemical properties and whatnot as well. So again, right, the force within is a covalent bond, not an intermolecular force, and the intermolecular force that is affecting HCl is a dipole-dipole force here. Other than dipole-dipole force, right, like what else could be affecting intermolecular force? And the second that we're going to look at is London dispersion forces. And so, when we have London dispersion forces, the idea is that the larger the molecule is, the more distortion we're going to have. And so this is kind of an example of our London dispersion force right here. We have two nonpolar molecules, but at sort of an instant in time, right, we end up having just some of those electrons swim to one side and some of them swim, so to speak, to the other, right? We just have these temporary distortions in the electron cloud. And when this occurs, right, if we should have a distortion of the electron cloud on this side of the molecule to the left, it's going to pull positive charge, which is to say push electrons away within the molecule that's nearby. And so when it does this, right now we have two instantaneous dipoles, and we're going to have a little bit of attractive force. And so, this force, right, it's not as strong as the permanent dipole force, yet it is strong enough to hold molecules together, right? And keep in mind here that when we are looking at our increasing intermolecular force, right, we can see that we have different, states of matter, right? When we have a larger intermolecular force at a given temperature, we will have a crystalline solid. And if we have smaller intermolecular force, we may have a liquid. And if there's really not very much at all, we're going to have gas, right? With respect to London dispersion, it's all about the size, right? If we have a large molecule, it'll have a big potential for these instantaneous dipoles and therefore a larger London dispersion force. If we have a small molecule, therefore, we are going to have a weaker London dispersion force, right? And so it's important to know that London dispersion force actually exists in all molecules, but it is the only force that exists in nonpolar molecules, right? Polar molecules have dipole-dipole force. London dispersion will affect all molecules because it's just about their size. And so again, this is the force that holds nonpolar molecules together. These instantaneous dipoles, temporary dipoles, London dispersion force. Okay, so let's take a look at the following, right? If we're saying which of the following do we expect to have the strongest London dispersion force, right? Remember, London dispersion force is dependent on size. So take a look at these and see what you think, and then we will continue. Notice that these are all in the same group, and the answer therefore is going to be the tin. And so if we look at this carbon family, right, and we look at their boiling points again, what we see is that CH4 has a boiling point that's way down here at negative 160. But the silicon has a slightly higher boiling point, and the GE has a slightly higher point, and the tin has the highest boiling point. And what this means is that as we're adding temperature, right, the intermolecular force within the tin is strong enough to hold the tin tetrahydride together until we're up at this higher temperature, right? And because there's this relationship, we're going to see that boiling point and the strength of intermolecular force are like completely intertwined, right? Because if something has a higher boiling point, that means that its molecules are not inspired to enter the gas phase until they have more kinetic energy. Whereas a low boiling point means that even with relatively small amounts of kinetic energy, we'll still have boiling occur, right? And so what is it that's holding these molecules in the solid or liquid phase? That is, again, the intermolecular force. And a boiling point is a sign that the temperature is enough that the intermolecular force has been overcome, and therefore higher boiling point means a stronger intermolecular force, and therefore we can see this pattern here based on size for this series. We can also see it just in the boiling point of alkanes. So these are all alkanes, right? These are containing carbon and hydrogen only, and the difference is in how many carbons are there. And so if we have things like methane, ethane, and propane, these are probably fuels that maybe you've heard of before, right? Maybe not so much methane and ethane, but these are like natural gas, right? If you have a gas line that's in your house or going, near your property or whatever, right? Don't hit the gas line or you pay for your gas bill. This is basically what it is, right? It's probably natural gas. And so, this gas, right, its boiling point is very low, so it's gaseous at room temperature, and we can, pump it into houses through pipes, and that's fine. Something like propane, right, we're getting a slightly higher boiling point, still a gas at room temperature, but what we can do is we can apply a little bit of pressure, and we can put the propane in one of those big, tanks you use for your grill. So something like, a Blue Rhino or whatever, if you've seen one of those, but, the big gray tank. And the way this works, right, is you put it under pressure, and when it's under a bit of pressure, so say we've got, 5 atmospheres or whatever, don't quote me on that, but some higher pressure inside the tank, most of it is going to be in the liquid phase, but as we learned about vapor pressure, there'll be a lot of vapor above the liquid phase. And so then, the vapor there, you let that out the top of your propane tank, it flows into your grill, and you basically have the same thing as with the methane and ethane, except you can put it under higher pressure so that it goes into the liquid phase and is just a little bit easier to transport, right? In this way, when your propane tank runs out, you'll notice there's really no sloshing around there anymore, not nearly as much as when you buy it, and it's nice and heavy. So moving up, we have butane, right, where this is like in little lighters and stuff like that. Boiling point is 0 degrees C. Doesn't need as much pressure as propane in order to have the same effect, right? Because again, we have these vapors that are able to come out of the lighter. You hit a spark, and there you have a little flame, right? Pentane, hexane, heptane, octane, these are liquid. Pentane, hexane, heptane, generally used as solvents, in chemical industries and otherwise. Octane, gasoline, some of these, larger ones are components of gasoline as well. Same exact reaction, basically, but now we are pumping liquid fuel into our engines, and we have internal combustion engine, which is able to use the gasoline in its liquid phase. And then as we get even higher, to C20, we have solids like waxes and things like that. And so we see here that all of these are nonpolar, and the boiling point varies greatly, right? We're going from something that's a gas at room temperature to a solid at room temperature all based on the strength of their London dispersion force, right? The smallest have the weakest and therefore are most likely to be gas at room temperature, therefore the most gaseous at room temperature, where the strongest London dispersion forces will therefore have higher boiling points and be solid at room temperature. So the last intermolecular force that we want to discuss is called hydrogen bonding. And so this is sort of a curious force, right? Where if we take a look at the series here that contains, this is sulfur, chloride, and phosphorus. So the ones that we're looking here, question mark, this is nitrogen, oxygen, fluorine, right? This is the HCl, one above that is HF, and so on. So we would expect them to be down here, right? That we have relatively similar polarities, yet we have a smaller mass, and therefore we have a lower boiling point. But that is not the reality. What the reality is that we have the boiling points have a huge jump, right? Ammonia has a much bigger boiling point than the rest in the series mostly, bigger than phosphorus trihydride, right? HF way above, right? H2O way above. And so, what is causing HF, H2O, and NH3 to have such higher boiling points, which does mean higher intermolecular force than the others in the series and in conflict with the carbon series that we just looked at. So, right, again, what causes this increase, right? Definitely don't memorize the theoretical one over here. This is just to say that is what we would expect if there wasn't something else going on, which is what we're about to look at. And again, what that is what's called hydrogen bonding. And this is somewhat poorly named, I would say, right? Because hyd bonding sounds kind of like a covalent bond, but this is not a covalent bond, right? This is an intermolecular force. What we have is the attraction of the lone pair that's on the nitrogen, oxygen, or fluorine with a hydrogen that's bonded to that nitrogen, oxygen, fluorine on another molecule. And so the idea here, right, is that the covalent bond, right, is between the nitrogen and the hydrogen, right? This is within water, within ammonia, within hydrofluoric acid. But what we're talking about here is this attraction between the lone pair and the hydrogen on a neighboring molecule, right? And again, when we have this here, what we see is that there is just a curiously strong attraction. And so, let's take a look at another hydrogen bonding network here for water, for instance. And for a question, see if you were paying attention, right? We see that there are hydrogens attracted to something on the oxygen. What is that on the oxygen that's attracting the hydrogens, right? And hopefully, if you were paying attention, there is a lone pair, right? And so, the origin of this hydrogen bonding, the reason why it's so much stronger than we would expect from the trend, why it's sort of an additional force, is that hydrogen is the smallest atom. And the HO bond, or the HN bond, or the HF bond is highly electronegative, right? There's a big separation of electrons within that HO, HN, or HF bond. And so because we have a nice strong dipole, and we have this hydrogen that's able to get really close to the neighboring molecule, we just have a much stronger force, right? Really based on hydrogen size. And so, again, remember from covalent bonds, we talked about when we have short bonds, those are strong bonds. That is the same principle here with hydrogen bonding as well, right? Because the hydrogen is able to get closer to the neighboring molecule, we have a much stronger force than we would expect, and we have this hydrogen bonding that's present. So again, sort of the long and short of it is if we have HO, HN, or HF, we have a hydrogen bonding intermolecular force, and that will be sort of the strongest of our intermolecular forces. And for just a little bit of additional context, right, hydrogen bonding is a big deal in our bodies, right? This is a force that is right here in the sweet spot where it is strong and it holds things together, but it's also reversible, right? We don't have to cleave covalent bonds that we have to bring back together that may not be as easy to bring together, right? There really isn't any chemical change that occurs in separating molecules apart and breaking hydrogen bonds. This is akin to a phase change, right? That when we have water that's boiling, that's overcoming the hydrogen bonding network in and of itself. And when we have water condensing, that hydrogen bonding network will reform, right? And that again would be this network that's shown here, where we have the waters that are attracted to each other. But of course, in the gas phase, they will be completely apart. And so in DNA, this is what holds the base pairs to one another, right? If we know that A is connecting with T and C is connecting with G, right? If you haven't had biochemistry or molecular biology, that is our adenine and our thymine connect to one another, and guanine and cytosine connect to one another. And they're able to be selective because A and T connect via 2 hydrogen bonds, while C and G connect via 3 hydrogen bonds. So in this way, they are matching, right? And they're not going to mismatch. And then also, right, being able to unwind and reform the DNA is very important, right? This is key to its function for, a lot of the function DNA has to do. It has this nice coiled up storage system, but storage is no good if you can't ever access it. So in unwinding and reforming our DNA, it's able to form all of its important functions. And this hydrogen bonding, therefore, is really critical to this very, very essential process for all of life. So not a biochemistry course that we're looking at here, but just some context to why hydrogen bonding is so unique and important, as well as just some context for what we're learning.